Hi everyone, my name is Haoran Zhu, and I'm a PhD student at New York University, advised by Professor Anna Koromanska. Today, I'm very happy to present our paper, Self-Supervised Representation Learning with Joint Embedding Predictive Architecture for Automotive LiDAR Object Detection. This paper has been accepted to AAAI 2026. The motivation behind our work is to learn robust self-supervised representations from automotive LiDAR point clouds. Most existing self-supervised methods rely on explicit reconstruction at point level. However, in practice, the assumption that there exists only a single correct reconstruction does not hold. Given a partial LiDAR observation, multiple plausible combinations may exist in masked regions. Using exact reconstruction can therefore limit its representation quality. To address this issue, instead of reconstructing raw signals, we propose to predict representations at a higher level embedding space. This allows the model to learn more abstract, semantic, and robust features. For example, given the visible parts of a car, such as its front, we aim to predict an embedding that represents the rear of the car, rather than reconstructing exact point-level geometry. We introduced Ad-L-Jepa, a joint embedding predictive architecture for automotive LiDAR. Ad-L-Jepa learns spatial word models by predicting bird's-eye view embeddings of masked regions using a context encoder and a predictor network. Importantly, our method avoids explicit reconstruction in point space. It does not rely on contrastive learning, and it does not require handcrafted positive or negative pairs. Instead, it focuses on embedding level prediction, which leads to a more stable and scalable self-supervised learning. The technical contributions are: it's the first JPA-based pre-training framework for autonomous driving. Autonomous driving data are sparse and scene-centric. We therefore focus more on non-empty regions and introduce a modified bird's-eye view guided masking strategy that enables prediction in bird's-eye view space. It's a paradigm shift in JPA from 2D image plan to direct 3D space. It leads to high-quality embeddings for downstream tasks and a faster pre-training time. Given a LiDAR point cloud, we first generate a mask in the bird's eye view space. This mask is then upsampled back to the original point cloud, producing a context point cloud, the unmasked points, and target point cloud, masked points. The context point cloud is fed into context encoder, while target point cloud is fed into the target encoder. Both encoders share the same architecture, consisting of a sparse 3D convolutional neural network. Since autonomous driving is largely a 2D problem, we reshape the 3D voxel representations into 2D bird's eye view representations. For the masked regions, we replace features with a shared mask token, and for empty regions, we use an empty token. These bird's-eye view features are then passed to a spatial predictor, which is a 2D convolutional neural network that predicts embeddings only at the mask grid locations. A known challenge in self-supervised representation learning is representation collapse, where all embeddings converge to a constant vector. To mitigate this, existing methods often apply a moving average update to the target encoder, where only the context encoder and predictor receives gradient updates. However, we empirically find that moving average update alone are not sufficient to prevent collapse. Therefore, we introduce an additional regularization loss applied at both context encoder and the predictor outputs. Our training objective is simple and effective: a cosine similarity loss between predicted and target embeddings, and a regularization loss. The regularization loss is essentially maximize the standard derivation, ensuring it stays above a predefined threshold. This explicitly prevents constant representations and stabilizes training. In bird's eye view space, most grids are empty, while only a small fraction contains points. This creates a significant imbalance during training. To address this, we introduce two weighting hyperparameters, alpha 0 equals to 0.75 for non-empty grids, and alpha 1 equals to 0.25 for empty grids. This allows the model to focus more on informative regions while still learning from empty space. We evaluate Ad-L-Jepa on LiDAR datasets of different scales, including KT3D, Waymo, and ONCE dataset. We compare state-of-art self-supervised methods such as occupancy MAE, and also we evaluate performance using 3D object detection as a downstream tasks. Across all benchmarks, Ad-L-Jepa shows consistent improvements over existing methods. Our ablation study shows that a masking ratio of 0.5 achieves the best performance. We further scale pre-training from 100K frames to 500K and up to 1 million frames on ONCE dataset. Ad-L-Jepa consistently outperforms other methods while being 1.9 faster in pre-training and 3 to 4 times more GPU memory efficient. Interestingly, we observe slight performance saturation when scaling from 500K to 1 million frames, likely due to data redundancy. This motivates future work on intelligent sampling strategies to select more informative pre-training data. We also analyze the sorted normalized singular values of learned representations. Compared to occupancy MAE, Ad-L-Jepa consistently maintains higher singular values across dimensions, indicating less redundancy, higher information content, and more expressive representations. In summary, Ad-L-Jepa introduces a new paradigm for self-supervised learning in autonomous driving. It efficiently learns robust LiDAR representations, achieves state-of-art performance in both representation quality and training efficiency, significantly reduces computational and memory costs. Thank you very much for your time.